Hey everybody. So, today I wanted to go through some conservation of energy examples. These really aren't that hard, but I didn't want to take our class time going through such simple examples. But if we skip over this, I think you would have a little bit of trouble. So, your homework for tonight is to follow through these problems. Write them down as we go. Get your calculator out. Fired up, ready to go. Are you all set? Here goes. It's conservation of energy examples. We're just going to do the front and back of the first page. First question. How much work is expended in dragging a 200 kilogram block at a constant velocity for a distance of 20 meters if the coefficient of friction is 0.35? Now, you're probably thinking, 200 kilogram block, that's huge. Yeah, you're right. You're right. But the key word that jumps out to me is constant velocity. So we're looking for how much work is done by expending a 200 kilogram block 20 meters with the coefficient of friction of 0.35. It's a lot of numbers and random information to organize. So I'm going to start where I always start, which is draw a picture. So here it is. Here's a block. It has a mass, and I'm applying a force to it for a distance of 20 meters, where mu is a relatively high 0.35. Now, if that's the only force acting on it, just me pushing it, then wouldn't it accelerate? Yes, of course it would. That's right. I almost forgot, but not really, to also account for the friction acting backwards. Now, there are two other forces that are acting on the system, on this mass. Guess we could call it a system if we wanted. We're going to have mg down and the normal force up. However, I think you guys see that we're only going to be worried about the forces in the direction of motion, which we're going to let that direction be positive. Now, work. What is work? Work is going to be equal to the force parallel times the displacement. Oh, well, we know the displacement. What's the force? Well, I know to find the force, all I really need is to find the force of friction. Because all I'm really going to say is the sum of the forces is going to be equal to 0 because it's traveling with a constant velocity. So plus this external force minus friction equals 0. So the force is going to be equal to the force of friction. I know you already knew that. I'm reviewing how to handle these problems. Now, if the force is the force of friction, I'm going to go ahead and substitute that in. So work, in this case, is going to be the force of friction times the displacement. Now that force of friction is going to be mu times the normal force times the displacement. Now, to keep going, what's the normal force equal to, you say? Oh, of course you already know that. Work is going to be mu, and the normal force is going to be equal to mg all times d. I know that by looking back at my diagram, and the normal force is equal to mg. So, take a look, and at this point, we're in that beautiful sweet spot of physics where we know all the numbers. 0.35 times a mass of 200 times 9.8 times d, which was 20 meters. Punch it into your calculator. I got 13,720. Maybe I'll round that to 13,700 joules. Good. Good. So in this case, that work in moving the block, because I didn't change its potential energy by lifting it up against gravity, I didn't change its kinetic energy because it was traveling with a constant velocity. The only thing that changed was that it moved, and while it moved, friction did work on it. So it converted the work that I did moving that block into heat and thermal energy. So now let's just find the kinetic energy of that baseball. I'm going to start with a picture. Piece of cake. Let's see. Here we got a baseball. It's traveling with a speed of 26 meters per second. And now, to find kinetic energy is just going to be 1/2 mv squared. Now, I think the only reason to even bother to do this problem is so that we can take a look at the units. So this time, I am going to include the units as I plug in my values. So 0.5 times 15 kilograms times 26 meters per second, quantity squared. So I punch that in. And I'm going to get 50.7. Now the units for that are going to be kilograms, meters squared, per second squared. Now, what does that equal to? Well, it's energy, so you know it should be in joules. But let's make sure that's in joules. Kilogram, I'm going to split it up a little differently. I'm going to write it as kilogram meters per second squared times meters. Yeah, some of you just saw it. Nice work. What does that equal to? Well, kilograms is mass. Meters per second squared, that's a measurement of acceleration. So mass times acceleration is a Newton. So it becomes a Newton meter. And a Newton meter is equal to a joule. So 50.7 joules. That was the point of that question. Next, find the mass of a rock with 280 joules of potential energy that is 4.2 meters above the ground. Now, at this point, I'm going to make sure that I say that at the ground, potential energy is 0, because potential energy is just a state function. So it has 280 joules when it is at a height of 4.2 meters. And potential energy due to gravity is just going to be m. Gosh, this is too easy. Too easy for you guys. I apologize. Now, I'm trying to solve for m, so let's get that all alone. I'm going to be quiet while you guys work through this. Oh, it's so nice and quiet, isn't it? Plug it in, get an answer. Don't be lazy on this part. Maybe that's why you guys are out of calculator shape. It's like when our coach would send us on town runs and I would hide in the cemetery. Do you think that really worked well for me? Actually, I didn't have to run, but it didn't work out well in the long run, did it? You guys, of course, got 6.8 kilograms. No problem. Good. Moving on. A pendulum type problem. A pendulum of mass 3 kilograms at the end of a 4-meter cord is raised to a height of 1.2 meters and released. What is the velocity at the bottom of its swing? And what is the centripetal acceleration of the bob, at the bottom of the swing? All right. So I'm going to draw a picture. Here it is at the bottom, and here it is when it is raised a height of 1.2 meters above the starting point. Now, because it doesn't really give us any indication about how high that ball is to begin with, I'm going to let the bottom of the swing have potential energy equal to 0. I can do that. Now, to find the velocity. In a situation where we are comparing position 1 to position 2, and we are not looking at any energy lost due to heat or anything else in the process, then we need to utilize, spit that out, that the total mechanical energy stays constant. So I know that the sum of the potential and the kinetic at position 1 is going to be equal to the potential plus the kinetic at position 2. And then I ask myself two simple questions. Is it moving? If the ball's moving, it has kinetic energy. I can't cross that out. Can it fall? If it can fall, if it's raised up above where the potential energy is 0, then it clearly has potential energy. So initially, can the ball fall? Heck yeah. It's raised up 1.2 meters. Is it moving yet? Nope. Kinetic energy is 0. At position 2, at the bottom of the swing, the potential is 0. And I go through this process of drawing in the whole formula and then canceling things out, because that's what we do in physics. Now, the potential energy is going to be mgh equals 1/2 mv squared. Oh, look at that. The masses also cancel out. Now, as I get v alone, I multiply by 2 by both sides. And I get v equals the square root of 2gh. So let's plug in what we know. C equals square root of 2 is 4.85 meters per second. Good. All right. Now, next it says, what is the centripetal acceleration of the bob? At the bottom of this centripetal acceleration, at the bottom of the swing, I just calculated it has a velocity of 4.85 meters per second. But here's the thing. A pendulum swinging like this is the same as a ball going in a circle. Picture it. It's the same bowling ball I swung in class, right? Just this time, instead of going a complete circle, it only goes in part of that circle. Also, the velocity changes as we go. But if I take a look, there's going to be a centripetal acceleration towards the center. And I can solve for that using the formula A equals v squared over r. I just found the velocity is 4.85 quantity squared divided by the radius, which is the length of the string, which is 4 meters. And I got 5.88 meters per second squared. Good. It's not so bad, is it? Maybe even too easy for you guys. Flip it over. Next. A swinging bowling ball has a total energy of 100 joules. How high does it swing? Oh wait, I can figure it out. It's like a question, then I answer. How fast does it go at the bottom or lowest point in its swing? All right, let's do that. So a bowling ball is going to swing back and forth. And obviously, we're ignoring air resistance. We're ignoring friction. I know that. I hope you know that. Otherwise, this problem will be pretty nasty. It says it has 100 joules of energy. So how much energy does it have at the first spot? Yeah, that's right, 100 joules. What's it got at the bottom? Yeah, 100 joules. What about here? Yeah, 100 joules. It just changes form. And when it is in position 1, which is what I'll label the first spot, it's going to be all potential. At the bottom? Yep. It's going to be all kinetic. What if it was in the middle? I know, then it would just be the sum of the potential plus the kinetic, obviously. Good. So how high does it swing? Well, if I want to find the height, I think I'm going to focus on position 1. Now see, I'm making this seem very simple, like how I go about figuring out what formula to use. I expect it takes you guys a little bit longer. Maybe not. But if I want to find h, that's going to be the potential energy equals mgh. Now the potential energy at position 1, it's all potential. So if I can do potential energy divided by mg equals h, let's plug those numbers in. I'm going to get 100. Good with that? I think you are. Now, how fast does it go at the lowest point of the swing? Well, at the lowest point of the swing, it's going to be all kinetic energy. So a kinetic energy equal to 1/2 mv squared. What are we solving for? Yeah, we're solving for v, aren't we? Just like over here, we were solving for h. So do a little bit of math. Twice the kinetic energy divided by the mass equals v squared. You guys are advanced, so I'm going to take that square root right there. Let's plug in our numbers. Now, hopefully this is going okay. Is this the most exciting lecture in the world? Heck no. Of course it's not. It's just practice. Is practice always the most exciting day? Nope. But is it essential for you to finally get it? Yep. I got 5.77. A velocity of 5.77 meters per second. Here we go. We're getting close. As two wild and crazy guys are riding a roller coaster, their car approaches a 14-meter drop at 9.5 meters per second. How fast will their car be traveling as they hit the bottom of the hill? The car and the guys have a mass of 330 kilograms. Okay. Sounds like we're in the middle of a roller coaster. It approaches a hill with a velocity. So we're not at the beginning. We're somewhere later on. And it says let's see. As two wild and crazy guys are riding a roller coaster, their car approaches a 14-meter high hill at 9.5 meters per second. Now, it says a 14-meter drop. So I'm going to say that it's at the top of that drop that it's traveling at 9.5 meters per second. What would be the velocity at the bottom of the hill? Ooh, you can see I'm slipping. It's getting late. It's 4:45. Getting tired. Been here since 7. Here we go. Conservation of energy. I know in the absence of friction and air resistance and any other forces acting on it, that the total mechanical energy should be conserved. So I can say the kinetic, usually I say potential first, the potential plus the kinetic at position 1 equals the potential plus the kinetic at position 2. And I did it right there without saying it. I made the top of the first hill position 1 and the bottom 2. Now, I asked myself the simple questions. Can it fall? Is it moving? In position 1, it can fall and it's moving. I can't cross off either one. At position 2, can it fall? Well, if I define the bottom of that hill, which honestly is the easiest thing to do, as potential energy equal to 0, then this term goes away. So now let's substitute in. And I make this look so easy, because it is, but it's just 2 formulas. Let's go. mgh1 plus 1 half mv1 squared equals 1 half mv2 squared. Now, many of you notice right away, I can divide through by m. Every term has an m in it. So I can divide through by m. I'm never showing that again. I'm just going to do it. So my next step, I've got GH plus 1 half V1 squared equals 1 half V2 squared. I got to bring that 1 half over, so now I'm going to multiply both sides by 2, and I'm going to end up with 2GH plus V1 squared equals V2 squared. Do you guys see it? I don't know if you do. I wish I could see your faces. Somebody out there might have just recognized that what we just stumbled upon was our second terrific trio formula, because it's all tied together. Now, if you saw that, awesome. Let's wrap this baby up. So V squared equals 9.5 squared plus 2 times 9.8 times 14. Now, I better take the square root of that after. And yes, I changed the order around a bit. You got this. I took the square root, and I got 19.1 meters per second. Anyone else agree? I hope so. Last one. Now, I know this is dragging on. I know it is. But hopefully it's just washing over you. As you write it down, you're like, I got this. This is soothing. Some of you right now are probably drooling on your keyboard. Wake up. Here we go. Last one. A roller coaster goes over the top of a 30-meter high hill with a velocity of 8 meters per second and drops to the bottom of the hill on the other side before rising to the top of an 18-meter high hill. How fast is it traveling at the top of the 18-meter hill? I think first I need to do a little bit of translation. So I got a hill, it goes up and down, and then it goes to a shorter hill. Oh, that's not so bad. Because it's a roller coaster, I try to make it look nice. There we go. And if I draw in my roller coaster cart, here it is at position 1. Here it is at position 2. Now there's a couple different approaches that I could take. I am going to choose to let the potential energy be 0 where I just drew it. That means the relative heights to that are going to be 30 meters for the first hill and 18 meters for the second hill. I also have a velocity that's given as 8 meters per second at position 1. Okay, reading the problem is most of the battle, because at this point I'm hoping you guys see that total mechanical energy, the potential plus the kinetic, has got to be conserved. So potential plus kinetic equals potential plus kinetic. Oh, is it moving in each case? Yep, it is. I'm trying to find what V2 is, actually. So it's moving. Can it fall in both cases relative to potential energy equal to 0? Yep. All right, so I can't cross anything off yet. So let's go. mgh1 plus 1 half m1v, no, just m, my bad. 1 half m v squared, v1 squared, equals mgh2 plus 1 half m v2 squared. All right, now this is AP Physics. So this is varsity. We got to solve for that variable. Mass is going to cross out. in order to add like terms, I'm going to subtract the other GH2 from each side. So GH1 minus GH2, I just subtracted it, guys. No big deal. Good. Good. Now, I can take many different paths and still end up at Las Olas when I get out of here. I can go out there and take a left, go out here, take a right. Same thing with algebra. I think I'm going to factor out a G. And then I think I'm going to multiply by 2. Yeah? Are you okay with that? Now, hopefully you weren't looking at the screen. Hopefully you just did it. Hopefully you're already done with this problem and you're just waiting for me to get out of here. Me too. 2 times 9.8 times the difference in the height. So 30 minus 18 plus the initial velocity, 8 squared, the velocity at position 1, equals v2 squared. Many of you are going to take the square root before you even write it down. Gosh, you guys are good. You're good. I went and took the square root as well, and I got 17.3 meters per second. Yeah? Okay. Now, I think that took too long, but you know what? It always does. Things that are worth doing take time. Such is life. So, what we did, at the beginning we did some simple work, kinetic energy and potential energy. Then we applied this idea of the total mechanical energy being conserved to some pendulum problems with a little circular motion review thrown in, and then roller coaster problems. I want to keep going. I do. I want to keep explaining. But you have had enough. Cue the music. Let's call it a day. Thanks.